Okay, good morning. So I want to go through these two problems. If you remember last time, we were supposed to solve these two problems. The topic was calculating high powers of matrices. And then this problem you were supposed to think about, and this problem. These are good problems, okay? And then we can switch the topic. So let us think about these two problems. I don't know how many of you have already thought about. If you haven't, please take your time and think about this example and that example. And then I will come back and try to solve these problems together. And then in the continuation it would be better if because from next time I want to give you some questions that you need to write down. It might be good to get familiar with this LaTeX system, how to typeset them. Of course, I haven't prepared lecturing about it, but we go through this together, and I think you can manage it easily. So that would be the what we are going to do today. Okay, so please take your time and think about these two problems. If you have forgotten, you can review my notes. There were 3 strategies to tackle high powers of matrices. If you have forgotten, review a little bit so that you can solve these problems yourself. Okay, so let us try to solve these two problems together, and then we can have some time to start getting familiar with the LaTeX typing system a little bit. So I don't know, did you manage to solve this one? Yes? So how did you do that? So A and B are commuting, and they are idempotent. Do you remember what is the meaning of idempotent? So when we say A is idempotent, it means A squared is equal to A. Yes? And it's mentioned that B is also idempotent. So I have referred the example in which I defined the meaning of idempotent. But from the content of that example, do you remember what is the property of an idempotent matrix that we discovered in those problems? Is that not only the second power is itself, any power of that is itself. This is what we did before. So now we want to calculate this one to a very high power. And if you remember what we did in the previous lesson, there are some strategies to tackle high powers. So one of them is starting to calculate some of the small powers to see if we can find a connection with the matrix itself, or I don't know, we can find a relation between some small powers of the matrix with the identity matrix, or if we can have a general pattern so that we can guess and then prove it using mathematical induction. Okay, so at least this is not very hard to start. So the first thing we are supposed to do is to calculate the second power, yes? Okay, but how do I calculate the second power? If you have some identities in mind, you can use those identities, or you can just simply expand it. But let me try to use the identities. I want you to be able to do this efficiently. So do you remember we had an algebraic identity for a plus b plus c to power 2, which is the first one squared plus the second one squared plus the third one squared plus 2 times the first one times the second one plus 2 times the first one times the third one, and finally 2 times the second one times the third. But you also hopefully remember that you have to be careful if you want to use this for matrices, because matrices do not enjoy commutativity in general. But of course, here it is mentioned that A and B are commuting. So when it comes to these two, I do not have any problems. But it hasn't mentioned directly in the problem that A commutes with AB as well. So you cannot take this for granted, yes? So there is no reason that I believe that A commutes with AB. There is no reason that I believe that B commutes with AB. We know that according to the problem, A and B commute. Okay, so do you think A and AB also commute? Because if I want to use that identity I just mentioned, I not only need A and B be commuting, I also need that A and AB is commuting. I also need that B and AB are commuting. Okay, so I have to check that one first. If you don't care about that, you can just write them 2 times and multiply them. But let us try to do them more efficiently. So the first question as I ask myself is A and AB is it a pair of commuting matrices? Okay, how can I answer the question? This is simple. I just multiply A by AB to see if it is equal to AB times AB. If this is the case, yes, then these two matrices are also commuting. But is it true or false? It is clearly true, yes, because for example, I start from the left-hand side, A, B. We already know that A and B commute, so this means that I can swap these two here, so then it becomes A, B, A. But I already know that matrix multiplication follows associativity, so I can take these pair of brackets and put them around the first one, and I immediately reach to the right hand side. So it was easy to show that A and AB also commute. For the same reason, B and AB also commute, yes? So you can also check that. So B and AB, I want to see if this is true that this is AB times B. Yes? So how should I do that? So again, I can start from the left-hand side, then this is B. Instead of AB, I write BA, or is it the case that, yeah, might be I use associativity first, sorry. I use associativity first and I write BA and then B. I put the pair of brackets around the first pair, and then I get this one, and then I can use commutativity to swap these two, so it becomes AB, B, and that's exactly the right hand side. So this means that yes, now I am on the safe side. Not only A commutes with B, A commutes with AB, B commutes with AB. So I can safely use that identity up there. So this becomes equal to the first one squared plus the second one squared plus the third one squared plus 2 times the first one times the second one plus 2 times the first one times the third one, but because this is negative, so it becomes 2a times ab, plus 2 times the second one times the third one, but because again of this minus sign, it becomes negative. Yes? Is that clear? Okay. But you need to remember, is it always possible to write ab squared as a squared b squared? If you remember, no, that was also one deviation from number algebra. But is it safe to do this here? Yes, because it is mentioned that A and B commute. So I can safely do that. So then it becomes A squared plus B squared plus A squared B squared. But you need to mention that since AB commute, I can write that. This I cannot change at all. But here I can use associativity and write a pair of brackets around the first pair, but then it becomes A squared. And here, minus 2, I can swap these two because this is commutative, it's commuting, sorry. And then B becomes close to this B, so this becomes B squared. Yes? And then let us simplify, because we know something more. We know that each one of these matrices are idempotent matrices. So instead of A squared, I can simply write A. Instead of B squared, I write B. Again, instead of this A squared, I write A. Instead of this B squared, I write B. And then of course here it's 2AB. And then instead of this A squared, I write A. Instead of this B squared, I write B. Yes? And then what happens? These 2ab is negative 2ab are cancelled, and then it becomes a plus b. But ab and ba are the same, so I can write this ab minus 2ab positive ab becomes negative ab. This becomes negative. So what happened actually? I calculated the second power of that matrix. Based on the assumption given to me, I was able to show that the second power of this matrix is equal to itself. It's a plus b minus ab. So this means that under these conditions, matrix A plus B minus AB is also an idempotent matrix. Yes? So when it is an idempotent matrix, this means that A plus B minus AB is idempotent. And based on the example referred in this problem, you know that any power of that matrix is actually equal to itself, not only the second power. So this is just simply A plus B minus AB. And of course, because A and B are not given to me directly, I cannot simplify more than that. That is the final answer to this problem. Is that clear? Okay. So you see, sometimes matrices, even though they look a little bit boring in the beginning, but they can also be interesting, yes? Of course, they are very, very important tools in our hand, especially when it comes to physics and, I don't know, computer science. So many, if we have time, probably we can also see that many, Google engines are based on matrices and linear algebra. So yeah, they are using these things very effectively. Okay, but let us go here. So what is the content of this problem? This tells you that you have a 2 by 2 matrix, any matrix that you like. We want to show that this matrix satisfies this quadratic equation. So exactly like this. For example, I can say that x squared, let us go back to the numbers. Okay, so I can write x squared minus ax equals to 0. Okay? I can say that show that a is a root of this equation, even though a is also involved here. So I'm saying that if you have this equation, show that the number a, which appears here, is a solution to this equation. So what do? You replace x with the proposed solution to see that if this is true or false. Okay, so it means that I replace x with a. Everywhere I see x, I put a. And then immediately you see that this answer is 0. So you confirm that whatever a is a solution. It's more or less the same thing that I'm talking here. I'm telling you that whatever a is, if it's a 2 by 2 matrix, this will satisfy this equation. And this equation, the unknown in this equation is x. So I'm just telling you that replace x with this matrix and convince yourself that the calculation leads to the 0 matrix. Yes? This is, by the way, it's called the characteristic equation of a matrix. I don't know if we have time to cover those topics here in this course, but this becomes important later. Okay, so let me now try to solve that. I don't think it's a hard thing. This is very, very simple. So I start from the left-hand side. I replace every appearance of this capital X. So I hope that you are not confused. X is not given. It's exactly like equations. I do not give you X, yes? So I have given you an equation. I am asking you to show this number A is a root of this equation. Exactly the same thing here. So this means that I replace every appearance of capital X with the matrix A. And then I have to do this calculation. But this is also a very straightforward calculation, yes? So this becomes a squared, which means A, B, C, D. A squared means the matrix multiplied by itself. So if you don't mind, let me write it 2 times. and then minus. Trace of A you already know. What is trace of A? Is the sum of the entries on the main diagonal. So this becomes minus, trace of A becomes A plus D, and then I multiply it by matrix A itself. And then AD minus BC is a number. Later, hopefully, we will see this one. This is called the determinant of the matrix. And I2 is a standard identity 2 by 2 matrix. And then we have to do this calculation. So if I want to multiply these two matrices, extremely simple. I take this row multiplied in this column, it becomes A squared, it becomes BC. I add them, it becomes A squared plus BC. I take that one and multiply it here, it becomes AB plus A will be multiplied here, B will be multiplied here. So it becomes AB plus BD. And I take this row multiplied by this column, so AC plus DC. And finally, I take this row multiplied by that column, so it becomes BC plus D times D is D squared. And then what I have to do here, so I multiply this number into my matrix. What it means that I have to take this number multiplied by each one of these entries. So if I multiply this here, this becomes A squared plus AD. If I multiply this by this entry, it becomes AB plus BD. Multiply this here, AC plus CD. And finally multiply this here, it becomes AD plus D squared. And this is also a number, I have to multiply it here. So this means that I have to multiply this number in each one of them. Of course, it is very simple. And then I have three matrices that I have to add and subtract. I have to do them entry-wise. So this becomes, I will take this number minus that number plus that number. So if you don't mind, let me write it down. So A squared plus BC minus A squared minus AD plus AD minus BC. Yes, so this minus sign goes for both of them. The next entry is AB plus BD minus AB minus BD plus 0. And the same thing here. So this becomes AC plus DC minus AC minus CD plus 0. And the final one is BC plus D squared minus AD minus D squared plus AD minus BC. If I haven't done something wrong, hopefully everything should cancel out. So A squared and A squared are canceled, BC and BC are canceled, these are canceled. So that's correct at least. 0. But AB and AB, BD and BD, that's also 0. So AC and AC, DC and DC, that's also 0. And hopefully the last one, canceled, canceled, and canceled. And that is 0, and that is the 0 matrix. So it shows that it doesn't matter what are the entries of your given matrix A, B, C, D, this matrix will satisfy this equation. Of course, that was not the point of this lesson. I gave this example here because mainly I want you to know how to use this, for example, to determine this matrix which involves high powers of the matrix A. Of course, I have engineered that in a way that you can use this. So that's a good idea to know how to do that. Okay, did you discover how to do that? What is the relation between part A and part B? Yes? Could you find any connection between part A and part B? Because you know that, I don't know, might be you have some experience with A-level questions or even harder Cambridge exams. So this is the system of designing questions. So you start with simple parts. Each part is a guide to the next part. This is very common in more prestigious exams. So you have a question that contains several parts, but in principle you should do them in order. When you solve the first one, which is a simpler one, and then you can use that as a guide for the second one, and then you can use both of them as a guide for the third one. So these type of questions are actually very common. So you discover actually an idea without the teacher just by doing an example. That's a very nice format of designing questions. Okay, did you discover the relation between these two? Why I have given these two in one problem? So my advice is that don't try to see everything. Okay, this is not easy in the beginning, but let us just try to understand. Okay, I have given you that any matrix satisfies this type of equation. In part B, this might be a little bit distracting for the time being, forget about that. But if I want to use part A in part B somehow, so I have to use this equation. Okay? Okay, this equation is completely generic. And now here I am talking about a particular 2 by 2 matrix. But this formula is valid for any 2 by 2 matrix, including this particular 2 by 2 matrix. Yeah, so what does it mean? It means that this will satisfy this equation. So this means that a squared minus trace of a, which is easy to read here, trace of a is 7, yes, times x, which is a, plus AD minus BC. AD minus BC is what? 3 times 4 AD minus BC is 3 times 4, remember 12, minus 4, which is 8. So this becomes plus 8, and I is equal to 0. Yes? So I want you to check it out again. Do you understand where this is coming from? In part A, I showed that regardless of the values that you choose for A, B, and C, and D, this equation is satisfied with the matrix A. So now in the second part, the matrix A is this matrix. So this matrix definitely satisfies a corresponding equation like this. Corresponding equation means that instead of capital X, I put A, but the trace of A is readable here, it's just 7. And AD minus BC is also doable here, it's 3 times 4 minus 4, which is 8. So this is something that probably I couldn't guess if this information was not given to me. Yes? But now I know that this is valid. Okay, but now how can I use this to answer the question mark? I don't think it's hard. You can see it, can't you? This matrix, somehow you need to understand the connection. Look at the first 3 terms in the question mark. What can I do in the first 3 terms in the question mark? Multiply by? This one. If I multiply this by 2, what about the powers? That's a correct idea mainly, but I want to do it a little bit differently. Yes, Aaron?
Can't you factor?
Yeah, factor instead of multiplying. Okay, so I factor these. Between these 3, I can factor a 2, but more than 2. So I can not only factor a 2, but 8 to the 8. And then what happens? From the first term, a squared is left. From the second term, minus 7a is left. And tell me what is left from the third one? 8i. Don't write just 8. It is meaningless. 8i. And then the rest of the story. Plus 3a minus 2i. Yes? But then, what is this guy? according to this, it is 0. So the hard part vanishes at all. Yes, I mean, this is just the 0 matrix. And this, everything is gone. And what is left for you is 3a minus 2i. But of course, 3a minus 2i is extremely simple to calculate for this 2 by 2 matrix. I just multiplied my matrix by 3, which becomes 9, 12, 3, and 12, minus 2 times I, which becomes 2, 0, 0, 2, and I subtract them. So this becomes 7, 12, and 3, and 10. Yes? So that is also a good problem. I just want you to give the idea that if you have an equation like polynomial equation for a matrix, this might also be somehow useful to calculate another polynomial of matrices. Okay, so that was the idea in this question. Okay, I hope that this is understandable. So I want to stop here. Next time we will continue the lesson, but let me just try to, I don't know how is a good way. Let me stop this video. Any questions about these? No?